All right. Hey everyone. Welcome to part 2 of optimal transport. In the last week, we discussed some of the theoretical foundations of the optimal transport problem. And today we're going to talk a little bit about the practical implementations of optimal transport and how we can actually use them in modern deep learning approaches. So, very quick revision or recap of what we covered the last time. Firstly, the optimal transport problem is effectively moving a sandcastle from one pile to the other, and you want to compute the cost of moving this sandcastle particle by particle in the most efficient way possible. And whatever that most efficient cost is encoded using a transport plan, which is basically telling you how much mass to move where, and that is in effect the optimal transport problem. We can apply this for a lot of problems where you basically have a geometric task. So, for example, neural style transfer, you have the color map of an original image and you want it transformed into the style of this artwork. You can do it using optimal transport. Similarly, there are applications in NLP, graph neural networks, medical imaging, where you use optimal transport to obtain better results or more consistent, more robust results with the same model, and point cloud matching. So basically just a set of geometric problems. We started by talking about how we can encode this in a more mathematical way, because saying moving sandcastles in some abstract space is quite an arbitrary statement. And we do this by defining a discrete measure alpha and another discrete measure beta, and we want to transform that original measure from alpha to beta, and that is encoded with some cost matrix. And then on top of this, we basically get our complete cost of transporting mass from input measure to the target measure. This is an example of that. And we discussed then the push forward and pull back operator. The important thing to note from that discussion is the push forward operator, where instead of moving one particle at a time, we move the entire sandcastle in one fell swoop. That is equation number 6. We are moving the entire measure space of x to the entire measure space of y, or the entirety of alpha to beta. We have pullback operator, which we will not require today, so I will skip that. And then we discussed the Cantor-Rovitch relaxation. Earlier, there were some problems with our original formulation, where we were basically assigning the total transfer of mass from some input to some target. And now we are basically splitting things up. We are saying we can break up a single input into multiple target locations. And that is basically the idea of the Cantor-Rovitch relaxation. It is incredibly powerful because it makes the admissible set of feasible solutions much larger than the Monge problem stipulates, which on the surface would make you think this makes it harder for us to obtain the optimal solution. However, it makes the problem a linear problem, and this is basically just our probabilistic transport that we have. So we define a feasible set of solutions using this coupling matrix, where we have P, which basically is sampling inputs that are non-negative and satisfy the mass conservation constraint, which is analogous to what we had with equation number 5, where the mass at the target for some valid transport plan T equals the sum of all of the inputs that are going to that target. So we can again visualize that using this on the right, where x4 through x7, all of the masses add up to become y1. So it is just a simple mass conservation constraint. If the mass is not conserved, which means if y1 is not equal to x1 plus x5 plus x4 plus x5 plus x6 plus x7, that means something is wrong with this transport plan. It's not a valid transport plan, and we can exclude that from our feasible set of solutions. So we have that, and this is the final optimization objective that we get after we basically do this process of relaxation, right? Where we are computing the cost again of moving some amount of mass to whatever the target is, but in terms of our cost computation, we don't really care as much, so we just compute cost times the amount of mass that we are transporting, right? And we minimize that. Once we minimize it, we get the new optimization objective. So we discussed this, and now we get into I guess some of the new stuff after this. Okay, yeah, no, also this. We spoke about how the this relaxation that we introduced to the original Monge problem is actually a tight relaxation, which means that even if we sort of don't, even if the optimal solution does not require us to perform mass splitting, that is deterministic transport gives us an optimal solution, the Cantor-Rovitch relaxation will recover that permutation, which makes it a tight relaxation. So it is a very, very strong solution that we have, or like a strong result or deep result that we have here. And because the coupling matrix P is symmetric, that means that you can basically reverse the transportation. So alpha goes to beta, and beta can also go back to alpha. The inverse always exists, which was not the case originally with the original Monge map, or at least not guaranteed to exist. Okay, awesome. So now let us talk about the dual formulation. The headline news from the Cantor-Rovitch relaxation is that our optimization objective is now a linear program, and a linear program has, along with the primal, also a dual problem, which again we discussed as an alternative problem whose solution upper bounds the primal problem. And if the upper bound is exactly equal, which means if it's a strict upper bound, then you have strong duality. But yeah, I think this is I skipped to point number 4 there. But yeah, the other interesting implications is that now we can solve the optimal transport problem in n to the power 2.5 log n using linear programming techniques. The optimal transport problem is now convex. And it has a dual, which is another linear program whose optimal value upper bounds the optimal of the primal. And if the optimal equals, we have strong duality. Now, if we know that there exists an optimal solution, we can choose to solve the easier problem between the dual or the primal and get the same answer. This it holds in a specific setting because we will sort of approach the primal and the dual as two different sort of problem settings, and in some cases it is easier to identify the feasible set for the dual problem than the primal, which is what makes solving one more feasible than the other. So the Cantor-Rovitch problem is a constrained convex minimization problem, but the dual is a concave maximization problem. Like the primal, we again have to define a feasible set. This set is now not a matrix, but a pair of vectors Fg, such that the element-wise summation, or the direct sum of F and G.
Oh shit.
You're good. The direct sum of F and G is lesser than cost matrix C element-wise. So from there we have the following dual problem where you want to maximize F dot product A and G dot product B, and these dual variables F and G are called Cantor-Rovitch potentials. Now for the primal problem, we had a sort of intuitive understanding of what the set of valid couplings were, right? We have the probability mass that is transported from the input measure to the target measure, and we want that mass conservation constraint to establish if a given coupling is valid or not. Now, we don't necessarily have that, but we can use an intuitive analogy. So consider the following hypothetical where we have an operator who wants to transport goods from warehouses to factories. So imagine warehouses contain the raw materials for some good, and by transporting it to the factory they can make some finished product. Now one way to optimize the cost of transportation would be to plan a route which is to just solve the primal problem. However, if the optimal plan is too expensive to compute, you're kind of in a dilemma because you do not know what to do. So one solution is to outsource your problem. A vendor can present to you two dual variables, F and G, where F is the unit cost of picking up material from warehouse label I, and G is the vector that consists all of the unit cost of delivering items to a specific factory J. So now you can sort of think of this like a menu card at a restaurant, right? You have all of the individual items, and you have the cost of ordering a specific individual item, but you do not know the bill at the end. It is easy for you to calculate the bill at the end, which is kind of what what the vendor can do over here, or where the operator can do over here, where the operator has their own cost matrix Cij, which means they know what the cost is for transporting mass from the warehouse to the factory. However, they don't know what that optimal cost is. In order to sort of do a soft check on the vendor's prices to see if the vendor can obtain a plan that is better than what they can do internally, the very simple check is to just add Fi plus Gj and see if it is lesser than Cij for all Ij. And now if you look at this equation just a little bit closely, you identify that this equation is exactly the same as the feasibility criteria, or the feasible constraint in equation number 12, right? Where we are performing the direct sum of F and G and checking that that matrix that we get at the end is element wise less than C or equal to. And if this is true, right, if equation 16 is true for all I and J, then the operator knows that there is no way that they can match the prices of the vendor, and they should definitely go with the vendor, because even if they solve the optimal transport problem themselves for their own cost matrix and execute whatever transport plan they get at the end of it, they will be unable to match the efficiency of whatever that vendor is. So that is an intuitive example of the dual and why it is relevant to consider. Do we have questions at this time? Everything makes sense? Alright, cool. Now we will talk about something that is incredibly important, and it is that optimal transport internally induces a distance. So if we fix C, we can compare measures and or histograms, it's the synonymous, by the cost of transporting the histogram or measure from alpha to beta. So we will effectively use a fixed function to compute distance at a pointwise level. So Cij is xi minus yj peak norm of whatever vector you obtain at the end, and you then basically lift this pointwise distance into a distance in measure space. So for example, you have 2 piles of sand again, right? And you want to identify how close these two are, right? Or maybe a more practical example, you have some y star, some target distribution that you are trying to replicate using some deep neural network, and y hat, which comes out of some neural network theta, right? You want to identify how close these two are to each other. One intuitive observation is that the shape of these are pretty similar, right? They both resemble the normal distribution. However, they are far from each other, and you can sort of see that because the means of both of the distributions are pretty far apart. So this y star minus y hat, this is pretty big, right? Just absolutely something greater than 0, whatever. This is an intuitive observation, but is there a way for us to encode that in a more structured way? And the P Wasserstein distance is effectively that way. It allows us to lift a distance in point space to a distance in measure space or histogram space, and then we effectively backpropagate against whatever distance we get in order to minimize the distance and have y theta basically be equal to y star. Okay, so in order for this, we need the cost matrix to, or the pointwise Cij to satisfy properties of a distance. As an example, let n equal m. So we have a square matrix here in our distance, or like in our cost matrix is a square matrix, and we can verify a couple of things very easily. Firstly, D in Rn by n is a symmetric matrix. The other Dij is equal to 0 if and only if I is equal to j. Both of these properties follow pretty directly from the from just the definition of the norm, right? We know that xij minus y xi minus yj is equal the pth norm of xi minus yj is equal to the pth norm of yj minus xi, and the by definition of norm it is 0 if and only if xi is equal to yj. So if I is equal to j, right? The other thing that is slightly harder to prove is the triangle inequality, and this is covered pretty well in the textbook in computational optimal transport. So this is linked in the first slide. If you want to check it out, feel free. But the main idea. Oh, question. Sorry, I didn't realize.
So you take the C is the P norm, LP norm, and then D is the square root of with respect to P of that. Is it not the other way around? Like C is D to the power of P. I'm a little confused about that. Why would you take effectively the square root of the P norm, the L?
Oh, we will take the square root over here.
No, I know, but like here you said C is equal to D to the power of P. Why is it not the other way? Like I'm a little confused about that because we define C as being the P norm.
Oh, it is not. It's not raised to the power of P. It's just the pth norm. D of P. D of the pth norm.
D of the pth norm.
It's not raised to P.
Okay.
It's not raised to P. That's my bad.
Okay, I was a bit confused. So what is D then?
That is just the distance metric that we are defining.
Okay, so it's the same thing as C.
Yeah, it is the same thing as C.
Okay, so I was a little confused about why you would take D is equal to C to the power of 1 over P. That's what I was confused.
Oh, okay. Yeah, you're good. Right. Okay, awesome. What was I talking about? Triangle inequality. Yeah. So the triangle inequality is proven using a combination of two things. One is the gluing lemma and the other is Minkowski's inequality. Both of them have a lot of background that I am not qualified to talk about, unfortunately. So you will have to take my word for it on this. But importantly, these three properties are in fact satisfied, and using this we define the Wasserstein distance, which is whatever the solution of the Kantorovich problem is, with taking C is equal to dp and taking the pth root of that, right?
Is the third condition just extended Pythagorean's theorem?
That is a triangle inequality, but you cannot directly apply Pythagorean's theorem.
No, it's just the extended version, the more general version, right?
Yeah.
For any like power greater than equal to 1.
Oh, not in.
Is that what they're like? I mean, that's what it looks like.
Well, okay, wait, maybe you can. Okay.
Maybe I'm wrong, but I just want to see if like that's the general idea.
Let's see.
Also, what's funny is in linear programming, the optimal transportation is all plagiarized from one textbook.
Really?
Yeah, that's what I was mentioning in the end. Is like every single textbook uses the same example.
Oh, you said that you liked it a lot.
Yeah, I liked it a lot, but like it's all plagiarized. Like that one example is all plagiarized from the original.
That's okay. Okay, here it is d to the power, or I guess this is just representational.
Yeah, that's just a weird notation. That's always been confused.
Okay. Yeah. Proof for P and Q are two optimal solutions. Stored issues. Yeah. Okay. The triangle inequality follows then from this. P and Q are two optimal solutions of the transport problem between A and B, and then B and C. Then you define a vector B such that if B is greater than 0, then this is 1.
I mean, it makes sense intuitively. All you're saying is like taking two paths has to be greater than or equal than taking the straight path.
Yeah, I don't know. Intuitively it follows. But if you want a more rigorous way of discussing that, I guess this is the proof. But
linear algebra.
it requires some setup. Is all.
That makes sense.
Okay, cool.
Sorry for the interruption.
No, it's good. More questions are better always.
Actually, I do have another, but I'm very sorry.
Yeah, no, sorry.
Do we have to use distance? Can we not use a similarity like kernel, for example, like RDF?
If you can prove that it satisfies properties 1, 2, and 3, you will have defined a new distance, and yes, it is completely valid.
It's just a metric space, yes.
Yeah. Oh, optimal this section is basically about how optimal transport induces, or like the metric properties of optimal transport. So yes, that's our topic. You came in late, so probably didn't miss the build up for this, but yeah. Okay, what was the question again?
No, I was just asking if you could apply RDF.
Oh yeah. If you're able to prove the three properties hold, then you should be good to go.
Probably doesn't apply to number 3.
I doubt, but yes.
RDF is weird, so.
If you can do some trick to prove that, you will have effectively defined another distance. So maybe try.
If I do find one, I'm writing a paper.
Nice.
That's for sure, but there's a problem.
Okay. Anyways, so this is one definition, and we don't have a visual like the other Mons and Kantorovich problems, but we still do have a couple of observations that are very useful. Firstly, WP, or the Wasserstein distance, is still very expensive to compute because we are still solving a linear programming problem in order to get the final cost, and that's not great. So we still have to perform some optimizations in order to make this perform better than what we currently have. The Wasserstein distance lifts LP distance from points to a distance between measures or histograms. So this is the big geometrically relevant result. And then third one, which is the not obvious one, which but more so exactly encodes the intuition that we were discussing from this part, is over Euclidean space, we effectively can factor out translations. So let T tau be some translation operator. We compute the expectation over the measure, or mean over the measure. In discrete space, it would just be expectation. And we now have the following. You have W2, where you are performing some translation over measure space alpha, another translation over measure space beta, and what you effectively get is again the Wasserstein distance with alpha tilde and beta tilde, and the plus the difference between the mean of alpha and mean of beta. So this is basically or like the second term is basically computing this term over here, where we are comparing the mean of both of the two distributions and obtaining the distance between those two. And W2 is basically the zero-centered version of alpha and beta, which means that we are now just comparing the shape of the two distributions. So if I overlaid one over the other and try to sort of compare the two distributions, you are performing this twofold comparison now. So you first explicitly compare shape and then explicitly compare how far the actual distributions are from one another. And this is incredibly relevant in order for situations where your default initialization is in very, very high dimensional space and doesn't have overlap, because the traditional way to approach this would be to just use a divergence term, right? So you would use scale divergence to compare two distributions. However, if I have two distributions that are incredibly close to one another but do not touch at all, right? So if this is alpha and this is beta, these two distributions will give you a KL value of positive infinity because there is a zero overlap, right? Similarly, I would say that say case number 1 is much better than case number 2, because even though assume for a second that the shapes are exactly the same and just the distance is different, KL will give you positive infinite for this as well as positive infinity for this, and these two are incredibly different. So if I were to go from 2 to 1, right, the gradient that I would get by computing the KL divergence with respect to my parameters theta is going to be 0, right? Which means the model does not value the closer distribution at all, but compared to these further distributions. So you have non-linearity in your gradients where it does not help you converge as easily, and that becomes a very significant problem in cases where you are attempting to train deep generative models, because you at initialization you are very likely to be very far from your target distribution, and not having any overlap means that your gradients are really bad, and if your gradients are really bad, you don't converge as well. So it is a compounding problem, and by using a distance rather than a divergence, you are effectively solving that problem ahead of time. A major consequence of that is that you are able to train generative models much better, and we will discuss the use of distance at least in an approximate setting with WGANs or Wasserstein GANs to correct for the above problem. So yeah, 2-4 comparison, which is basically what I illustrated earlier.
Alpha and beta are the ways that you could recreate the distribution, right? They're like all the parameters of the distribution, like you could have variance or...
Think about why. Oh, you mean
like alpha and beta here? Those are just descriptions of the distribution itself, right?
Yeah. Alpha and beta is the measure, right, that we were discussing earlier.
Which measure?
Like we were discussing, you have discrete measure. Remember, like this, where at point x1 you have mass a1. Oh. Okay, mass a1 at point x2 you have mass a2, and then so on and so forth, right?
Mm-hmm.
So this is the discrete measure that we're working under. So you can just consider either the continuous case or just a highly discretized version of alpha beta. That's it. Okay. So it's that same thing. If we want a practical analogy, we can consider just y star and y theta. You have y star being target distribution that you want as the output, and y theta being the output that your model gives you for a particular input, right? So we want to approximate y star as closely as possible using the neural network.
No, I'm going to come back to this.
Right. Okay. You're good. Please do not say sorry for asking questions. These are very good questions. Okay, awesome. And then other things like variance or just other properties of the distribution, that is covered in that first term, because we are still comparing Wasserstein distance between alpha tilde and beta tilde. So that's the shape versus the actual mean of distribution comparison. Okay, awesome. So now we can address the first point from slide number 20, where we talk about how the p-Wasserstein distance is still expensive to compute, and we want some practical way of computing the Wasserstein distance. So one special case of optimal transport is the one-dimensional case. This is going to start off a little bit tangential, but we will basically generalize the one-dimensional case to the n-dimensional case and use that to effectively create a new distance, which we will call sliced Wasserstein distance, which is quicker than n to the power 2.5 log n, which is what we need in order to compute the p-Wasserstein distance. So one special case of optimal transport is the one-dimensional case. X is just your set of real numbers. Assuming the case where you have uniform weights, so over here A1 is equal to A2 is equal to AN for all AI, and Cx is just the x minus y to the power p, so the pth norm raised to p. We have two measures, alpha and beta, the input and the target measure, and the only place that actually matters is the points now, right? Because the mass is exactly the same. So we kind of are back to Monge map territory, but we will solve just with the standard Kantorovich relaxation. So without loss of generality, we can assume an ordering on each of these points. So x1 is lesser than or equal to x2, and so on and so forth for 1 through xn. Similarly, we can do the same for our target measure, y1 is lesser than y2, and so on and so forth, all the way to y through n. Right? Now, we have already solved our optimal transport problem just like this, where if we just set our transport plan of xi to be equal to yi, we get the optimal solution. So this is a very interesting result, because for the one-dimensional case, in order to obtain the optimal transport plan, really all you have to do is sort x, sort y, and just associate xi to yi, and you have solved the optimal transport problem. You are guaranteed to get minimum cost. It may not be the unique, it may not be a unique solution, but it is going to be an optimal solution, and that is pretty cool. Also, before that, the generic case also holds and is more involved. I'll show you all a visual of that, but effectively it is the same. It is in practice what you're doing is you're just kind of treating the x's like a stack, where you fill up the mass of y1 using as many x's as you need from 1 through whatever points, whatever number of points it takes to fill up y1. Then go to y2, y3, so on and so forth, on up to yn. So multiple x's can contribute to a single y1, or one x can partially contribute to it, but effectively the same thing. Cool. Alright, so now we have a closed form transport cost. Closed form in quotations, because we still are performing the sorting over the operation, but we can compute p Wasserstein distance directly like this for the one-dimensional case. So this reduces optimal transport to a sorting problem, can be solved in n log n, which is awesome. So here is the visual for both uniform and the generic cases. So for uniform, you are basically assigning the entire mass of point, say x1, which is the first one, to the first y1, and so on and so forth, all the way to the end. For the non-uniform setting, where mass is distributed unevenly, you just kind of fill up the as much mass as you can to complete y1. And if y1 is completed, which means x1 is greater than y1, you just transport more mass all the way to the next y2, and then so on and so forth. So kind of like filling a set of glasses with another set of glasses, and the glasses are of uneven size.
Why does alpha and beta change size here? Shouldn't one of them remain constant?
Pardon, I don't.
Like, why do alpha or beta change size in your visualization?
These are two different examples, right? So one example is the uniform case, where each of the x's have the same weight. So a1 equals a2 equals an, right, and b1 equals b2, and so on and so forth.
No, I see. I thought they were like the same case.
Oh no. Yeah, this is
I didn't see the first one.
this is like the footnote from here, like where we discussed the generic case in this slide, right? But we discussed the setting where all of the weights are just uniform, but that's not a very strong result by itself. But it holds for the generic setting as well. So that is something that was relevant or not. Okay, awesome. This is nice, but again, it is still somewhat limited, because it only allows us to solve this in the one-dimensional setting. can we extend this notion to Rn? And the idea here is we slice and dice. We project n features onto d random directions, and Rn in this case is our measure, right? Our measure is an n-dimensional measure. D is a hyperparameter, so we are sampling from the unit circle uniformly d random directions, and now we project the n features onto those d random directions. We effectively get d one-dimensional optimal transport problems as a consequence of that, right? Then we sort those d lists and obtain the d optimal transport plans. We compute the average cost of transportation over all of those plans, so all of the costs, and just mean it up, and we get our result at the end. The major caveat is that now what the distance that we have obtained is no longer the P-Wasserstein distance. It still satisfies the properties of a distance in measured space. However, the geometry that is induced by the P-Wasserstein distance is different from the geometry that is induced from the sliced Wasserstein distance. In the continuous setting, we don't have to consider randomly sampling d directions from the unit circle, because we effectively just integrate over the entire unit circle. So we get all of the directions or projections for all of the directions, average or obtain the expectation of cost over the entire unit circle. So we get the continuous setting. It gives us a much more concrete non-random definition of the sliced Wasserstein distance. But if we want to empirically apply it, we need to obviously make some sort of compromise, right? So this is that. All right. So here is what that looks visually for a single direction. You have PV, which is the target, and you are projecting your measure in R2 in this case along that direction. You obtain P tilde V, which is like the output of your model, and that is in itself a projection. So we are projecting along the same direction for both the target measure as well as the input measure, and then we individually sort the input as well as the target measure, then just compute the difference to get our final distance. And we do this for a bunch of directions in order to get a consistent distance value. Crucially, this sliced Wasserstein distance that we obtain is differentiable, which allows us to use optimal transport to optimize neural networks to generate textures. So, for example, we have this texture of a leopard, and we can see that it generates something pretty similar. Similarly, for this, you have like a scale-like pattern, probably for like a cushion or something. It generates something that looks pretty similar. Question?
So I'm still a little confused about what you're actually sorting here.
Yeah.
What is actually PV and P tilde V?
No. So PV is the direction that you are sampling, or like the projection along the vector V, and V is being sampled from the unit circle, right? Yeah. Okay. No, that's fine. Does up to here make sense?
No, like I don't know what you're actually like sorting.
Okay, yeah, no. Just think about one-dimensional problem to start with, right? The sorting is happening in equation number 20. We have measures alpha and measures beta, right? X1 through xn is the points in my input measure, and y1 through yn is the points in my target measure, right? Those are what are being sorted. So just you have a collection of points, right? Collection of points that are colored in red is your alpha measure, and the collection of points that are colored blue is your beta measure, right? You just sort them to get an ordering of the collection.
So we sort them along the direction here in one dimension. Okay.
Right, yeah. Maybe if I can write this down. So I have x as say 3, 4, 1, 0, right? And for each of these points, I assign mass of 1 over n, so this is going to be 0.25 for all of these, right? So all of these have mass of 0.25, and similarly I assign y of 9, 7, 1 and 14, right? Just arbitrary points in R1, right? Now I will sort x over here, I will sort y over here, okay? And I will claim that my optimal transport plan is simply this I will define as y bar, and this I will define as x bar, and I will claim that my optimal cost of transportation can be determined by taking some x bar I and just outputting y bar I.
Do you need as many y's as x's?
For this case, yes. For this case, because we are defining just uniform mass, right? But if you don't define uniform mass, it is like the analogy of filling up the cups, where you need to have the total mass obviously remain the same, which is guaranteed by property of measure. But you would basically transport as much mass as possible from xi or x1 to y1, right? If you have excess mass remaining in x1, you will transfer that remainder to x2 and so on and so forth until x1 is expended completely, and you keep doing that until you go through all of your xi's. If xi is smaller, then you will just proceed to the next xi and keep filling the target y, whatever y sub j, until y sub j achieves that target mass, and you just keep doing that one at a time until you have populated all of the mass, which is what is happening in example number 2, right? You transport all of the mass until everything gets filled up completely. That makes sense?
I think so.
Okay, so now this is our setting that is working in the one-dimensional case. But now we want this to work in the d-dimensional case or the arbitrary dimensional case, and we do this by projecting the measure in whatever d dimensions into this real number line by identifying or sampling a vector from the unit circle and then projecting the measure onto the direction that we sampled.
You mean the unit circle, like nth dimensional circle, right?
Yeah. Unit circle in the end, in the nth dimension. Exactly correct. Yes. Yeah. So in this case, we have our measure in R2, so we are sampling from the unit circle. It will be the unit hypersphere for d dimensions, n dimensions, right? So now we project the measure onto the sampled direction, and we get again just a single real number line, correct? And this we then sort. So we have all of these points over here. That is just, again, one is larger than the other, right? We sort this individually, and then we just claim this original transport map over here, and we just say that this is the optimal plan, which is why in order to compute the cost, we need to just do that third subtraction that we do, and then compute the 2 norm squared, and that's it.
So you take 2 sortings.
Yeah.
And then what's the minus sign here? Because like, what does it mean, like, to minus the sort? Element wise,
after you sort, you get a sorted array, right? So you get a sorted array after sorting x is x bar, and then another sorted array after you get y is y bar.
Well, you're sorting PV and
yeah. When you get PV, right? It is in one dimension. It is R1.
Is PV not just x and y? Are you not sorting all x's and all y's in one direction? Do you know what's happening?
That is exactly right.
Oh, so it's p like x and p tilde y? Is that what's happening?
Oh, P is the projection onto V. V is sampled, right? The left projection is the target, and P tilde is what our neural network is outputting.
Oh, so yeah, it's x and y's. Okay, I thought those were already like input outputs. Okay, so P to V.
It is input output.
What?
Yeah, like this is again, it's R of 2, right? So the alpha beta thing that we were using, red is no longer alpha, blue is no longer beta. Like that, that doesn't hold anymore.
Well, isn't the right side your whatever your original distribution is, and
Yes,
the left side
the right is the distribution the output distribution that you get from your neural network, and the target is the one on the left.
So we want to make it like the left.
Yes, we want to make it like the left.
Okay, and we start with something like the left. Okay, that makes sense.
Yes, yeah. So we project both. After we project both, we sort both of them, and that is the equivalent of sorting these two, right? And then we want to compute the cost of transportation, right? So we simply just follow this equation over here, 21, right? Which is just xi minus yi.
Right, that's just the distance. I see.
Which is what's happening.
They're doing it very greedily afterwards. It's basically whichever one is closest, I think, right?
I don't follow. What do you mean by?
Well, how do you choose which one goes to which in your sorts? You sort an OT, right? Like after you've sorted them,
Yeah.
you perform an optimal transport between the two.
By sorting them, you have already performed optimal transport. Sorting them is the performing of optimal transport in the one-dimensional setting.
Can you demonstrate that? I'm a little
Yeah, that is over here. That is what we have over here.
But here, how would you decide, for example, that the big leftmost circle in your second example
Yeah.
would go partially to the first one and then to the second one?
Second example, right?
Yeah, second example.
Okay. So I fill up. I start with this x1 over here, and I start with this y1 over here. Okay. I have more mass in x1 than I have in y1.
So you just do a 2.0 approach.
Yeah, exactly. Just fill as much as you can until it reaches the target mass. Once it reaches the target mass, you move on to the next one. So x1 sort of expends out a fraction of its mass and satisfies y1's condition. Then it moves to y2. Y2 is x1 does not have enough mass remaining. It fills up y2 with whatever it has. Then you go to x2 and you see, oh shit, x2 also does not have enough. So you go to x3 and now x3 does. So it transfers all of its mass and you get y2 sorted.
Does this satisfy the greedy property? Like it feels pretty greedy in a person.
Could be. I'm not certain. Can't give you a definite answer.
I don't know if there, I don't know. This seems too good to be like true and optimal. Is there no edge case?
I don't think so.
Oh.
Yeah, this is probably optimal solution. So the solution you may get may not be unique, but it is the optimal. The cost that you get is going to be optimal for the one.
One is that it will it does follow like a greedy type of a solution where you're just assuming because how the argument would go for you're assuming suppose that there is another solution that isn't optimal. That's suppose basically you're saying okay, I have a greedy assignment, right? And then suppose I have another optimal solution that is an additional assignment that differs from greedy, right? So the whole point is that by this claim, you basically get a contradiction where this other your claimed optimal solution, right? It must have basically an equal it must have an assignment of equal cost as the greedy solution, effectively.
Yep.
That's basically how this would go. This is basically a greedy type of problem.
Yeah, but I don't visually see the proof right now.
Well, it's hard because it's hard to think of it as visually. The whole point is that you're saying, okay, this is my greedy algorithm. This is how I assign the values, right? How it was described here, right? You just greedily, take the one on the left, fill it up on the right, right? And they're saying, okay, now suppose there is some other assignment, and the whole point is that assignment, you basically show that it will have an equal quote-unquote cost as your greedy assignment.
I think in the book, the way they structured the proof for this was in a very, very generic setting. They said let y1 be lesser than y2, y2, and then x1 be lesser than x2, and then they said that the difference y1 minus x1 is let me make sure I'm remembering this correctly. Yeah, no, I don't remember what the approach was, but they kind of they swapped out. So yeah, the
you can also think about it as okay, how about here's another way you can think. You can think about it inductively, right? So you have your two assignments, right? X is 2 Y's, right? And you're saying induction, right? You're saying, okay, take the first step, take the first point where for X, I'm assigning different values, right? And the whole point is that now your claim here is that, okay, greedy, right, has this cost. My other solution, I'll call optimal, right, it'll have this cost, right? Now the whole point is that you're saying, okay, if optimal assigns to a different node that has a higher cost than greedy, then that's a contradiction. Because I claim that optimal was assigning the optimal point, right? So therefore, I can swap it, right?
Yeah, no, what I'm saying is like there could be a way, like the problem with that argument is you're assuming that the optimal would take a better approach first.
Oh, but that's how you define optimal. So you're defining optimal as this is the lowest cost assignment I have.
Yeah, but what I'm saying is like here you're following. I guess it works because this is convex.
It's not even convex, it's just like the structure of all greedy proofs.
This also works for uniform cases, so the convexity is not a factor.
Like it's just like a proof structure. Like you're just assuming that you have two assignments basically.
Well,
how can you know that the optimal solution, when you do your first assignment, will get a better result or equal than greedy?
It's by assumption. You know that optimal is one assignment.
But you, like, it's the same
guys, maybe we should save this discussion
sorry.
for a bit later, for sake of time. But yeah, there is a proof. We can go over this probably after through the book and understand exactly what is happening there. But it is an optimal solution. We slice and dice it into some d directions, d being some hyperparameter, and we are able to get a new distance as a consequence of that. This part makes sense. Assuming slice Wasserstein distance is probably an optimal solution. All right, awesome. The next problem that you suffer when you use slice Wasserstein distance is that you lose a spatial prior by projecting into random directions. So, for example, if you have something like a checkerboard where you where the spatial pattern of the input distribution is very, very relevant, you want to retain that. So the standard approach to solving slice Wasserstein distance loses it where you have the same distribution of black and white or blue and red. However, that does not look anything like a checkerboard, and that becomes a problem if you have any task that requires this spatial reasoning. For a texture, not so much the case, but for spatial problems, this is much more relevant. So the way they solved this was very simple. They added an additional dimension, and basically what that does is it effectively restricts sorting to each of those subgroups. So they sort within red, sort within blue, and that effectively just results in solving the optimal transport problem twice for both of these distributions, and that is just solving both of those problems separately and within those own internal spatial structures, and that results in the new texture that you get resembling the spatial prior that you manually basically specify. Awesome. We have this, and then finally Wasserstein GANs. So we have the following setup with GANs. You have a discriminator as well as a generator, and normally your discriminator is going to give you some probability of that input image being real or fake between 0 and 1, and your generator is giving you an output image from some latent space RZ. Now the difference between generated and target, the generated and the target distribution is minimized using divergences by default for traditional GANs, and like we compared in this example over here. Gradients are not always informative when we are using divergences. So the Jensen-Shannon maximum value is log 2. So if you have parallel lines that are infinitesimally close to one another, the divergence between those two is going to be the maximum value that you can get because it relies on having some form of overlap in order for it to work. Question?
Is Wasserstein distance symmetric?
I believe yes.
Okay.
Probably.
I'm assuming it is.
Right.
Why I'm asking is like in the problem like Jensen-Shannon, why it's introduced is because KL is not symmetric.
Yeah. I think distances are symmetric by property, right? And Wasserstein distance is a distance in measure. So yes, it is. It should be
It must
symmetric.
be symmetric.
Yes, exactly. But yeah, that right. So instead of using a divergence, what if we use a distance? And that is the main intuition behind Wasserstein GANs. In implementation, you don't get exactly that. You get something that is slightly different from it, where you basically hope that your new discriminator, which outputs just something in the real space, models Wasserstein distance implicitly, and this is shown to work to an extent. I have the following algorithm, which I am going to try and share, or the, like actual code implementation, which I'm going to try and share using my computer. So give me a second here. Okay, good. Oh, I guess I can't train it right now, but let's see. Model is fairly straightforward. This is just the discriminator is just a traditional conv backbone, and the generator uses a single linear layer to transform a latent space into into a spatial map, and then you have a transpose backbone to increase the number of channels at another conv backbone to reduce it down into one. And we are training to generate images from the MNIST data set. Yes?
What's the transpose backbone?
The transpose layer is just you're increasing the size of your spatial map.
Oh, okay.
Okay. So okay, yeah. And the training code for this is basically now the algorithm 1 that we have over here. I am pulling the data as normal, and this is just that data loader. We are sampling from the prior over here, and we run training for a specific number of iterations. So this is the critic iter or the disk iter, which is effectively the same thing. We train the model to maximize the distance from or maximize the output of the model, which we sort of structure it to be the distance. So we are computing the some real value of fake x, which is the image that is generated from the latent space, and you have the actual real image that you have sampled from your data set, and you are basically just trying to maximize the two. So you basically want to say that these are two images that are far apart from one another, right? And you run this for a couple of iterations, and then you do the same thing, but in reverse, where you have your okay, so this algorithm is actually a little bit different, and I'll get into the details in a second. But the idea behind the generator, since we are positing a game, is you freeze your discriminator and try to get your generator to increase the value of whatever the discriminator is outputting, which means that the image looks as close as possible to the original image distribution, and this ends up resulting in much more linear gradients. Now, there is one interesting property in the code in line 7, which is basically you are clipping the weights of the discriminator, and this is because what ended up happening in a lot of cases for this original paper was that the discriminator ended up becoming way too powerful, so they kind of just lobotomized the discriminator by freezing values to be a maximum of positive C and a negative of negative C, and a minimum of negative C, which in our case is 0.01. And that ended up apparently working well, but when I tried to replicate their experiments, just one second, it did not end up working as easily. So I made a couple of minor changes. Firstly, I made the formulation much more dynamic, in the sense that you establish a threshold of distance you want to create between your critic, and once it sort of achieves that distance, once it creates a gap that is still surmountable, you move on to the generator, and then the generator closes that gap. Once it closes that gap, you short circuit the number of iterations. So you have multiple iterations for the generator as well as multiple iterations for the discriminator based on whatever threshold is set. And I removed the clipping and replaced IMS prop with Adam, and finally, finally, the other thing that I also did was I also established a benchmark set of values for some real inputs that were sampled earlier, and I basically said or prevented the notion of overshooting the target, because the generator is trying to maximize the value of the discriminator for the fake samples. If you are overshooting the input, you inadvertently end up making the result further from the target distribution, because the target distribution is sort of fixed or learned at a particular value and is not positive infinity necessarily. So by just constraining that, I was able to get pretty good performance without needing to weight clip. Alexi, you had a question?
Yeah, I was going to ask what was RMS prop.
Just an old optimizer.
Okay.
I don't think it's used very often.
I was confused for a bit, and then you explained it.
Okay.
Two moments that you add.
So this is the training with the standard GAN, and I did not perform a lot of hyperparameter tuning. I just tried a couple of random learning rates, and it does not work very well. This is just standard, the standard generation after a bunch of iterations. The sample generation after a lot of training, and I think maybe there was a slightly better option. Obviously, we know that this works because there have been papers that have been published with working solutions. But the point was to demonstrate that it is not straightforward like the hyperparameter tuning is a huge process with this case. Versus with the WGAN, we observe much quicker convergence to something that actually looks like numbers, and then if you train it for a little bit longer, you actually start to see things that make sense. So this is iter 129 out of 500, and I'm too lazy to go all the way to the end, but effectively it starts to look like it makes a lot more sense very, very quickly. So that's a general idea. I did not have to perform any hyperparameter tuning on it. This is well for the first set of epochs, for the first learning data I chose, which is an order of magnitude larger than the one that I demonstrated for standard GANs, which shows the value of better gradients. These are the same architecture, it's the exact same architecture, but the performance is radically different, and the range under which you actually obtain convergence is also radically different, which is part of the reason why optimal transport is very, very relevant in deep generative models in general, and something you should really, really care about. So yeah, that is all I had to talk about today. Thank you so much for your time. Hope you have a wonderful rest of your day. If there are any questions, I'll be around. Thank you.